In order to understand Einstein's relativity, we should consider sound waves and light waves. Let's see what the similarities are and what some of the differences are. So sound can be described as a pressure wave, which propagates outward from a sound source in all directions. The speed of sound in Earth's atmosphere is approximately a constant 343 meters per second. It's constant regardless of the motion of the object emitting the sound. Now, first of all, let's draw some air around an object. Air is made up of particles. And let's say that the particles are fairly evenly spaced. That's reasonable to assume. Now, what happens if the object starts oscillating? Let's say that it is a diaphragm which bows in and out very rapidly. What would that look like? Well, if it were to expand in size, then that would cause a lot of air particles to be pushed into a space where they wouldn't normally be in. It would create high pressure. Around the object. Then let's say that the object suddenly contracts into a very small size. Then what would we have? Well, we would still have this high pressure ring. So we would have this high pressure ring, and there would be a low pressure space where the object used to be. Now, when our particles are near each other in a place where there's high pressure, and then let's say that next to that is a place of just normal pressure, then those particles are not going to want to stay there. What will happen is the energy will radiate outward. They'll want to move from high pressure to low pressure here. So as they bump into particles around themselves, what we'll get a spreading out of rings of pressure around the object that's oscillating. So there's a high pressure ring. Out here we can have a high pressure ring. And so on. Here's our object. This is called a crest when we have a ring of high pressure. And a trough would be a place where there is low pressure. And according to the speed of sound being 343 meters per second here, our sound wave will naturally spread out nice and uniformly. So that's an example of a stationary object that's oscillating. But what would happen if we had an oscillating object that's moving? Say, for example, you're standing here and you throw an oscillating object toward a friend who's going to catch it. At first it's located here, and let's say it's vibrating in and out, disturbing the air around it. Then what would happen? We'd have this ring. So at t equals 0, there would be a disturbance. And then sometime later, that disturbance would travel outward in a spherical shape. But let's say that your object is moving with constant velocity toward the catcher, maybe something like this. It's changing its position. So the place where the air is getting disturbed is changing too. First, we disturbed the air here. Next, we're going to disturb the air there. So at t equals 1, the disturbance will travel outward. And later in time, the disturbance could look something like this. Then, at t equals 2, this point becomes the source of our disturbance. And so it would look something like this. The point is that the crests become very compressed in front of the object that's moving, and the crests are very spaced out behind the object that's moving. Does that change the speed of sound, though? What is the speed of this crest? Well, it turns out that the speed is still 343 meters per second. It doesn't matter that the object is moving. However, the Doppler effect says that the person who's hearing those crests will notice a difference in the sound that they perceive, as opposed to if the object wasn't moving. So what they'll hear is they'll hear a high frequency, a higher pitch. And we also see that there will be low wavelength. The wavelength is the distance between the crests. It has the letter lambda. Frequency has the letter F. So what should the person over here hear? Will they hear a high frequency or a low frequency? Well, assuming that these wave crests still travel with the same speed, the number of crests that hit their ear per time will actually not be that high. They will hear low frequency on this side. And there's a large wavelength. The critical takeaway from this, though, is that the speed of sound is constant, even if the frequency or the wavelength changes. And there's actually a formula that relates them. The formula is the speed of sound equals the lambda, the wavelength, times the frequency. So this will stay constant. If the lambda, the wavelength, goes down, then the frequency has to go up. If, on the other hand, the lambda goes up, as it does on this side here, then the frequency goes down. Now let's compare this to light. In the 19th century, physicist James Clerk Maxwell summarized the laws of electromagnetism into 4 concise calculus equations called Maxwell's equations. They're pictured above. Maxwell analyzed the solutions of these equations and arrived at several significant findings that led Einstein to be able to develop his theory of relativity. The solutions of the equations turned out to be electromagnetic waves. They were sines and cosines. He found that light itself is an electromagnetic wave. Maxwell said that these waves in a vacuum can only travel at one particular speed, and that is the speed c. C is the speed of light in a vacuum, and it's approximately 3 times 10 to the 8th meters per second. So a similarity between sound and light is that they both have constant speeds of propagation. But one major difference between the two is that unlike sound, light doesn't need a medium to propagate. It can travel in a vacuum where there's no material at all. Now, another thing that sets light apart from sound is that Einstein recognized that light speed is not just constant relative to one inertial reference frame. Instead, his special theory of relativity is based in part upon the fact that light travels at a constant speed in all inertial reference frames. That's a very profound statement and one that could be challenging to understand. So to demonstrate a little bit about what it means, you have to think about Galilean relativity. Like, let's say that the catcher here is actually going to be on a moving cart now. And let's say that they're headed toward the wave crests now. Let's say that they're moving at 343 meters per second towards those crests. How fast will they perceive the sound to be coming at them now? Would it still be coming at them at 343 meters per second? Or would it be coming at the person faster? Like, would they still hear the same frequency as they heard when they were stationary? Or would they be hitting the crests more rapidly because they're moving? And would they hear a higher frequency? According to Galilean relativity, they would perceive the sound to be coming at them faster. They would believe that it was coming at 686 meters per second now, because they're moving in an inertial reference frame. But what Einstein said is that that wouldn't be the case for light. Einstein said that even if you're moving at an object, the light doesn't come at you faster than light speed. It can never come at your eye any different speed than c, which is 3 times 10 to the 8th. It can't come at you slower than that, and it can't come at you faster than that. It's very profound. But it is one of the important assumptions of Einstein's theory of relativity.